In this video, I'm going to be talking about vectors. Now, a vector is a quantity that has both magnitude and direction. And some common examples of vectors in physics would be displacement, velocity, acceleration, force, among many others that you'll learn about throughout this course. I want you to notice that above each one of these vectors, there is a symbol, an arrow. That arrow is used to denote a vector quantity. Now let's compare vectors to scalars. Scalars are quantities that are described only by magnitude. For example, they do not have any direction, only magnitude. So some examples are distance, speed, time, and mass, among many others. So when we say distance, we do not have reference to the actual direction. When we use speed, we're not giving the direction. So I'm going 60 miles per hour, that's my speed, or I'm going 60 miles per hour south. Notice that include both the magnitude, 60 miles per hour, and the direction, south. So, the direction is indicated with a sign, positive or negative, or a cardinal direction, as I just gave in my example of east, west, or in my case, south, or a relative direction, up and down. And I'm going to explain these to you now. Vectors are expressed graphically as an arrow. And the length of the arrow is proportional to the magnitude. That's going to be very important throughout this course. So, for example, here I have a vector quantity of 3 meters, and that is a positive 3 meters. I have here positive 1 meter. Notice that the length of the arrow is approximately 1/3 of what it was for my 3 meter vector. Also notice the signage is positive. Now, let's compare that to negative 3 meters. So this is going in the opposite direction, and negative 1 meter, the arrow points in the opposite direction. So our positives and negatives correspond to directions that are relative. For example, I could say positive 3 meters, or as you can see from this vector, I could also say 3 meters to the right. Or I could say, for this one here, negative 1 meter, or I could say 1 meter to the left. The point is that you're not going to say both. You're not going to say negative 1 meter to the left. You're going to use one or the other, whichever one is most appropriate. So, moving on, and now let's go ahead and look at up. Up is relative. So we can use that. We can say 3 meters up. We can say positive 3 meters, which implies 3 meters up if we are defining up as the positive direction. We can also look at our Cartesian plane, and we can say 1 meter south. All right, so one is a relative direction, and the other one I'm using a cardinal direction, which I'll talk to you about in just a minute here. Again, look at the length of the arrow. Notice they are proportional to their magnitude. In other words, the greater the magnitude, the longer the length of the arrow. And of course, they point in the direction either up, or in terms of the Cartesian plane and cardinal directions, south. So if we look at a vector, again, this gives you your visual. Magnitude, length. The direction that it points is the direction for the vector quantity, and we will typically call the arrow either the head or the tip, and then the opposite side the tail. And I'll be talking to you about that a little bit more in the next podcast. So on the Cartesian plane, we're going to use something called cardinal directions. Now, you know cardinal directions. You may just not have heard them called that: north, south, east, west. We're also going to be looking at angles relative to the Cartesian plane. So in this case here, we have a vector quantity that it can be described as a given magnitude, and then the direction would be 45 degrees, okay? Now on the Cartesian plane, for cardinal directions, 45 degrees can also be referred to simply as, in this case, northeast. 45 degrees over on this side, northwest. My point here is 45 degrees can be specifically referred to as northwest. And this will become a little clearer as I move on to angles that are not 45 degrees. Southwest, what's the angle implied? 45 degrees for all of these. And of course, southeast also implies at a 45-degree angle. So let's go ahead and now compare that to an angle that is not 45 degrees, like this angle. Theta is equal to 60 degrees. Well, in terms of our cardinal directions, we would describe this direction for this vector to be 60 degrees north of east. So pause the video, take a minute and think about this. 60 degrees north of east. Now you might be thinking, this is northeast. Technically, northeast in itself implies a 45-degree angle. So anything different than 45, we have to describe it as such in terms of the cardinal directions. So 60 degrees northeast. What about this angle, phi? Well, in this case, phi is equal to 30 degrees. So pause the video, see if you can describe this using cardinal directions. So we get that this is 30 degrees east of north. 30 degrees east of north. In other words, the direction for this vector in terms of cardinal directions on a Cartesian plane can be described as either 60 degrees north of east, or we can also say 30 degrees east of north. Both of those are perfectly acceptable and accurately describe the direction. The Cartesian plane, again, if we are looking at angles other than 45 degrees, for example, 20 degrees, how would we describe this in terms now of relative directions? In other words, we're not using cardinal directions here. This is relative to a given frame of reference, a given position. So in this case here, we would describe this angle theta as 20 degrees in front of the negative y-axis. That would be an acceptable way to describe this relative direction on the Cartesian plane. Here's another example. Here we have 20 degrees above the positive x-axis. Now, we will use these mostly in the kinematics unit, but it's very important for you moving forward in this course to have a good idea of what vectors are and how to use vectors, not only for describing direction using cardinal directions, a plus sign, a minus sign, but also relative. Let's talk a little bit more about relative directions. Here we have an object that is projected. It is launched. It is launched at a 40-degree angle above the horizontal. Okay? See how this describes the direction relative to a position or the horizontal position. Here we have a pendulum, and its angle is 40 degrees as well, and it is described as being 40 degrees from the vertical position. So that's two more ways to represent the direction of vectors, but using relative directions. So to recap, we can use signage, plus, minus. We can use cardinal directions, east, south, west. We can use relative directions, up, down, to the left, 20 degrees above the positive x-axis. All of those are great ways for describing the direction of vector quantities. So our College Board big idea here is having students be able to represent forces and diagrams mathematically using labeled vectors with magnitude and direction, and of course units for the analysis of a situation. And I'll see you guys in class.